Let's get ready to do some math. Hey folks, all right, back to AP Calculus instructional videos. Hopefully this is making sense to you, okay? This is new for everybody, this virtual learning. So please email me with any concerns, okay? Make sure when you watch these videos, you pause if you need to, write things down. You can hear me say things again. I think it'll actually be a big help for some people, okay? But do the best you can with stuff like this. Join my Remind as soon as possible, okay? At some point, pretty soon I'm going to have to assess whether or not you guys are actually doing any work or try to take attendance and things like that. Remind might be a way to do that. I might have to set up a Google Classroom. Okay, so watch the website. Please try to follow the directions. If you have concerns with anything, please email me. Best way to get in touch with me. We're continuing our work, okay, with differential equations. 1.1 was solving differential equations. We're actually talking about 1.2 today, and that's Slopefields. Slopefields, an important topic on the AP exam, sometimes pretty easy types of questions, sometimes some difficult types of questions. Okay, so we'll speak about Slopefields today. And what a Slopefield is it's really a way to model a general solution. That's what we're doing with the differential equation. You're given a derivative, okay, and you solve for y. With a c involved, that's a general solution. Then if they give you some kind of information about the function and a niche condition, you can solve for c and get that particular solution. But the Slopefield will actually graphically model a general solution, which is really a graphical model of an infinite amount of particular solutions. Okay, so really, a Slopefield right here. Let's talk about a Slopefield. Now, how they're going to actually, model, infinitely many particular solutions, they're going to do it using the derivative, using the slope, okay? A Slopefield is really just a collection of pieces of little tangent lines, okay, that model a general solution. So we could say a collection of pieces of tangent lines, a collection of pieces of tangent lines, that model a general solution, that model a general solution. Sir. Remember, a general solution right there is going to have that plus c, really represents infinitely many particular solutions. Infinitely many particular solutions. Or soluciones, if you want to say it in your best American Italian. So what the heck does the Slopefield look like? Well, if we start and we actually maybe draw a particular solution, okay, so I don't know, maybe a graph that looks like this, kind of looks like the sine curve. If you draw a bunch of pieces of tangent lines, okay, to the curve, the idea is that if you remove the actual function, okay, so you leave the axes there, you remove the function but leave the tangent lines. On my smartboard, I could just take this, actually remove the function, leave the tangent lines that way. Here we'll kind of have to, draw it out the best we can. But you can see if you just leave those tangent lines there, you get a pretty decent approximation of what the function looks like. And remember, we're going to have that c here, for a general solution. So maybe the c represents the y-intercept. Maybe another particular solution is this guy shifted up 1 unit. So if you draw the tangent lines, probably look like a little something like that right there. Maybe another particular solution is this thing shifted down 1 unit. So maybe it ends up looking like this. And a Slopefield is actually a collection of a bunch of pieces of tangent lines here that model a general solution. They model infinitely many particular solutions. So maybe it'll end up looking a little something like this. Okay, and you'll see there's two different types of problems they do on the AP exam. Sometimes they want you to come up with the Slopefield yourself. Sometimes they give you the Slopefield, okay? We'll come up with the Slopefields ourselves today. Tomorrow we'll worry about when you're actually given the Slopefields. But you can see there are a lot of different particular solutions that could be drawn depending on what your niche condition is. If they tell you a point that lies on the function, maybe this point right here, then you should be able to get a good approximation for what particular solution they're talking about, okay? And the good thing is that when they want you to actually draw out these Slopefields, you're not going to have to draw this many tangent lines, okay? That's going to take forever, but eventually you're going to have a bunch of tangent lines on there when they give you a problem, maybe something like that. Then you can see we're talking about a Slopefield right there. They won't have you draw one of those out, but you'll have to actually, identify what differential equation corresponds to that Slopefield. Let's slow it down. get a little ditto action going. Hopefully you're downloading these dittos. Hopefully you can find them easily. Let me know if there's any problems like that, any logistic problems. We need to work on these things. All right, so you guys can get the best instruction possible. But here, slope fields, sketch a slope field for this differential equation, dy over dx equals 2x at the 9 points indicated. So they're actually going to give you points, and they're going to want you to sketch a tangent line, okay, at each point. Now, how are you going to do that? Well, if you want to draw a little tangent line, you got to get the slope of the tangent line. Slope of the tangent line, that means the derivative, which they're going to give you, by the way. That's the differential equation. But, maybe we'll do like 6 dots here before we actually jump into that first problem. Basically, if you could figure out what the slope is, which you can by plugging into the derivative, you should be able to draw a tangent line. Remember maybe they tell you the slope is equal to 0. Okay, if you plug in an x and y value, you get a slope of 0 back. That means that's a horizontal tangent line. So draw a little horizontal piece of a line right there, okay? I feel like that looks like it's sloping slightly downward. So wherever Hannah and Matt are, they're probably laughing at me right now, but I want to redraw that. Do the best you can, make it a horizontal line. They want to see it's horizontal. Don't be lazy and be like, yo, there it is. Okay, draw it out nicely on the AP exam. So that would be a slope of 0 right there. Maybe you have a slope of positive 1. Do the best you can to draw that slope. Okay, 45-degree angle, sloping upward like that right there. Shouldn't be the worst thing in the world. You could do a slope of negative 1. Maybe you plug in, you get back a slope of negative 1, perfect 45-degree angle, sloping downward. Do the best you can. Maybe you get a slope of something like, 2. And that's going to be a positive slope heading upward, but it has to be steeper than the slope of 1. So they're not going to be able to perfectly see what your slopes are, but they're going to compare them. If you have one slope that's equal to 1, another slope that's equal to 2, they're going to want to see that this one is steeper. Maybe get a slope of like negative 1/2. Right, which means it's going to slope downward, but not quite as steeply sloping downward as the negative 1. Okay, so do the best you can. Today we'll see a situation where the slope is non-existent. Well, there's a lot of different things that could happen. There could be a sharp point there. There could be, a point of discontinuity. There could be a vertical tangent line, which is usually what they're talking about, but they won't ask that on the AP exam. Okay, so this really won't be on the AP. Won't be on AP. So try not to worry about that, but it's going to show up when we're talking about today. So I figured, why not mention it, right? Why sub-zero? I mean, why not? Where my physics people out there getting that joke. So back here, okay, if you actually want to draw a slope field at a differential equation at these 9 points, you could see that this slope right here is only dependent on x, okay? So dependent on x. So really, it only matters what the x-coordinate is to actually get the slope, So if you want to, you could actually lump these points together because you don't want to waste time doing this on the advanced placement exam. It could be really annoying plugging in separately. You make one little silly, computational mistake. They're going to take off all the points. So you want to be careful, but you also want to be efficient, okay, the way we always are in here. You can see this point, 1, 0, this point, 1, 1, this point, 1, negative 1, they all have an x value of 1. And you'll see if x is equal to 1, then dy over dx is going to be equal to 2 times 1, which is going to be 2. Okay, so I know I'm going to have a slope of positive 2 at this point, at this point, and at this point. And all those slopes should kind of look, those little tangent lines should look parallel there. Do the best you can. It doesn't need to be perfect, okay? But, when you could actually lump together points like that, do that. Like these 3 points right here, they all have the same x-coordinate. They have an x-coordinate of 0. If x is 0, 2 times 0 is 0. So let's draw a little snippet. Do the best you can. Not easy to see right here. Okay, because of these little tick marks. On the AP exam, it'll just be the dot, like this right here. So it'd be easy to see if you're drawing a horizontal line. So those are horizontal lines there with the slope of 0. And you can see all these points right here have an x value of negative 1, which means the slope is negative 2. So opposite of what your slopes were over here. And that's how you sketch a slope field, okay? If you want to see, what this means, what's the conceptual understanding here, let's actually solve the differential equation. Lots of practice with solving differential equations. You need it. Everybody needs it. Let's talk about it. Let's try to separate. First thing we do is cross multiply. Always put the dy on the left-hand side. dy times 1 is dy. dx times 2x is 2x dx. And you can see we're already separated, okay? So we can integrate both sides. Remember, keep the left-hand side as clean as possible. Already pretty clean right here. Integral of 1 with respect to y is going to be y plus c, but we put that plus c on the other side. And that's somebody's derivative in there. What do you take the derivative of to get 2x? A little bit of x squared. all right, plus C. And that right there, I can't do any better, okay? I don't know what an initial condition is, so I can't get a particular solution. This is a general solution. Sir. If he was in the Navy, he'd be an admiral solution. All right, that's terrible. But anyway, here, depending on what C is equal to, this is just going to be y equals x squared, either shifted up or shifted down, or maybe not shifted at all if C is equal to 0. This is a family of parabolas. We are family of parabolas, don't you see? Anybody else losing their mind in quarantine? All right, so family of parabolas, a lot of times they'll give you a slope field on the AP, and then they'll tell you the initial condition. They'll say, 0, comma 0 lies on the function, so that would be this point right here. Really, you can't see that at all, okay, but I'm doing the best I can. That point right there, they'll ask you to sketch the particular solution. You want to kind of do the best you can to follow those tangent lines, okay? It's not going to be easy, but it doesn't need to be perfect. And it would look a little something like that, which would make sense, right? Because if C is equal to 0, the point 0, comma 0, set y equal to 0, set x squared equal to 0, you'll get that C is equal to 0 when you solve. Well, then it would be y equals x squared, this parabola right here. Maybe you end up solving and get C is equal to negative 1, right? Which means now it would really be x squared minus 1, which means it'll look a little something like this. And you can see how it's following those little, tangent lines right there. Maybe they tell you that C is equal to negative 2. We didn't even do that point, but maybe they do. They tell you it's a point right here. Then we're talking about y equals x squared minus 2. Not done great right there, but close enough for government work. Maybe they tell you C is positive 1. It looks a little something like this. So we can see how it's a family of parabolas, and infinitely many in between, right? Maybe C is equal to negative 1/4, something like that. The parabola would look like that, okay? Something important about this is that when you see these slope fields, you might notice that if you look in a vertical line, the slopes are the same for this particular slope field. And that's because this slope field is dependent upon x. And a lot of times, they'll give you the slope field first. And if you see that you see the same slopes in a vertical line, that means I don't care what y is equal to. It doesn't make a difference if you change y values, if you stay at the same x value, because you're going to have the same slope. But if you change from one x value to another, then those slopes are going to change, okay? So if you see that you have the same slopes in a vertical line, that means you're dependent on x. That means same slopes in a vertical line. And that could be important because they're going to give you a slope field and they're going to want to know which differential equation, corresponds to it. And if you see the same slopes in a vertical line, then you know that the differential equation has to be dependent upon x only, which means that any differential equation that has a y in it, you could knock out of the multiple choice. We will talk about that more tomorrow. That's very useful dependence, okay? So we'll talk about it more and more as we go. How about here, speaking about dependence, we can see this differential equation depends upon y only, okay? So dependent on y. That actually means you're going to end up seeing the same slopes in a horizontal line, okay? And if you take a look here, horizontal line, look at these points, okay? These 3 points right here, they all have a y value of positive 1. I only need the y value to get what the slope is here. You can see if y is equal to positive 1, dy over dx is equal to 1 minus 1, which is 0. So each of these points right here, as long as the y coordinate is equal to 1, the functions that we're describing, that infinite number of particular solutions, all going to have a slope of 1 right there. These points right here all have a y value of 0. When y is 0, dy over dx is equal to positive 1. So slope of positive 1 for each of these. Do the best you can with that. And down here, we got a slope y value of negative 1, which means the slope is going to be 1 minus negative 1, which is really 1 plus 1, which is 2. All right, so a slope of positive 2. Make sure it slopes upwards, even though I'm drawing them with a downward. You could draw it this way to make it slope upward. Make sure that you have more steep of a slope than you did for the slope of 1 over here. So hopefully actually drawing out the slope field is not too terrible. We won't solve this differential equation because you could really get into it, and the problem is manipulating with a C right there. It gets really filthy. This is also something known as limited growth, which we don't do limited growth. We only do exponential growth in here. We'll be doing that in a couple days. So we're not going to solve the differential equation, but maybe they tell you that, the initial conditions, they give you initial condition, and they tell you it's the point, let's say, negative 1, comma negative 1. So they're telling you -1 comma -1 is a point on this function, and maybe they want you to draw the particular solution with the initial condition -1 comma -1. So -1 comma -1 is going to be a point on the function for sure. You want to draw the particular solution. Do the best you can, okay? Try to actually follow those tangent lines right there. And maybe it looks like a little something like that. You know, it kind of looks like here with the slope of 0, you have a horizontal asymptote. That's not always true. You could have a bunch of, parabolas or something like that, and that's their minimums. But, do the best you can. It kind of looks like you're leveling off to an asymptote, which you are here. If you solve this differential equation, you get something known as limited growth. Exponential growth is unlimited, right? Shoots upward. Limited growth is actually going to level off at some value. But even more important than that, look at the slope field right here. If you move in a vertical line, the slopes change. Before we moved in a vertical line, the slopes didn't change. That meant that we were actually dependent upon x. Here we move a vertical line, we're changing y values. You could see the slopes actually change. If you actually move in a horizontal line, you're changing x values, you could see the slopes remain the same. So I don't care, if you change x values, the slopes don't change because this thing is not dependent upon x, it's dependent upon y. So remember, dependent upon x is the same slopes in a vertical line. If you see the same slopes in a horizontal line, that means that you're dependent upon y. So same slopes in a horizontal line. And that's important because they might just give you a slope field and you realize you have the same slopes in the horizontal line. Then it's actually going to be dependent upon y, the differential equation. So if you see dy over dx equals 1 minus x or something like that, you can knock that out of the multiple choice. More on that tomorrow. Here, if we take a look at number 3, that rhymes with me, and that's who I am. This differential equation, let's sketch a slope field. You could see this one's dependent upon x and y. So now we need to be a little bit more careful because you need to know what the x-coordinate is to get the slope and the y-coordinate. You're not going to be able to group them together. You're not going to see the same slopes in a vertical line or in a horizontal line. Remember, the way to do this is to keep the negative upstairs to make it a little bit easier. It's really up to you. But this gets annoying, right? Plugging in. If I actually plug in this point right here, x is 1, y is 1. -1 divided by 1 is going to be -1. Here, this point, 1 comma 0, x is 1, y is 0, which is kind of interesting because that's -1 over 0. That's non-existent, which is probably a vertical tangent line. Not always, and you won't see one like this on the AP, but it's kind of cute what happens. And then if you actually plug in this point, x is 1, y is -1. So -1 over -1 will give you +1. And be careful with that, okay? Do the best that you can when you're plugging in. If you need to write it down a little bit, be my guest, okay? There's a lot of, kind of filler in the way here. You could write it down if you want to, but you could burn a little bit of time. But remember, the main operation here is to actually get the problem right. Here, these points are all great because x is 0. Here, x is 0, y is 1. So -0 divided by 1 is going to be 0. This point's a little weird because x is 0 and y is 0. So we get -0 over 0, which is 0 over 0. That's indeterminate. So if it's an indeterminate slope, you can't determine what the slope is yet. You can't write it yet. I wonder why the slope there is indeterminate. We'll figure out in a couple minutes. Here, x is 0, y is -1. So -0 over -1 is going to be 0. Over here at this point, okay, we can see that x is -1, y is +1. So -1 divided by +1 is 1 divided by 1, which is +1. Write it down if you need to. Sorry if that was fast. You can always just pause the video. When you hit play, we'll be right back here for you. Here, x is -1, y is 0. So -1 divided by 0 is 1 divided by 0, undefined. It's a vertical line in this case. You won't see it on the AP. Here, x and y are both -1. So the negation of -1 is +1 divided by -1 is going to be -1. So it should look a little something like that. Maybe you're thinking about what do the particular solutions look like. Maybe you're thinking right now and you kind of have the idea in your head. Don't tell anybody. Let's actually solve this differential equation. Okay, so get a little separation going on, cross multiply, put the dy on the left, y dy. Well, y dy, because y times dy is y dy. Terrible joke. Okay, over here, dx times -x dx. And you can see they're already separated. You got to keep them separated. Bow, 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 bow. Don't know if you know that song. Anyway, let's integrate Don't differentiate, get it straight. Okay, integrate y to the first. You can see it's y squared over 2. Don't forget about that plus c. We'll put them on the other side. Integrate negative x to the first, negative x squared over 2 plus c. Add some cookies right there. And remember, I don't solve for y until I solve for c, which I can't do here, right? Because they don't, give me an initial condition. But that's just using an advanced algebraic technique. I could clean this up a little bit. I can get rid of constants on the left-hand side, multiply by 2. Multiply by 2 on the right-hand side as well. So y squared over 2 times 2 is going to be y squared, equal to negative x squared over 2 times 2 is negative x squared. And remember, c times 2, a constant times 2, just another constant. I won't solve for y here because I'd have to square root both sides, right? I don't use any advanced algebraic technique until I solve for c. But it's even cuter if you actually add x squared to both sides. And now we end up with x squared plus y squared is equal to c. And that's something you should actually recognize, okay? That's actually a general solution that represents an infinite numbers of what shape? Very good. Circles, okay? In a circle that has center at the origin and a radius of radical c, believe it or not. So this right here is a family of circles. We are family of circles, don't you see? Okay, so a family of circles right there. What did I just write? Circles. How do you spell circles? I don't know, something like that. Okay, so a family of circles, and you can see if the initial condition is maybe 0, 1, this point right here, think about what the particular solution would look like. Okay, probably a little something like that. Beautiful little circle. Maybe the initial condition is the point 1, 1, this point right here. So if you want to draw that circle, what is it going to look like? Probably a little something like that. And you can see it's really just a bunch of concentric circles, bigger circles and smaller circles. Bullseye. And you can see why we got indeterminate slope at 0, 0, because that's the center of the circle. Okay, so a little something to think about there. Moving right along, okay, if you keep looking at your dittos, here's a nice AP problem from the 2000 AP. Okay, it was actually a BC problem, believe it or not. Okay, but you can see something like this on your AP quite easily these days. Consider this differential equation right here. They want you to sketch a slope field for the differential equation at the 11 points indicated. So look, this differential equation dependent upon x and y, you're gonna have to plug in x, you're gonna have to plug in y the entire time. So it can get a little daunting, but try to group things together. Look, all these points have y equal to 1, and if y is equal to 1, we get 1 minus 1, which is 0. 0 squared is 0. I don't care what x is equal to, okay? X times 0 is always going to be equal to 0. All these points have a slope of 0, so you can lump things together that way. Even these 3 points right here, or maybe just these 2 points, they have an x coordinate of 1. So x is going to be equal to 1 over here. Multiplying something by 1 is not going to change its value. So you can just focus on the y value. The y value here is 0. 0 minus 1 is negative 1. Square negative 1, we get a positive 1. You could say times 1, but it's still positive 1. Plug in a negative 1. Negative 1 minus 1 is going to be negative 2 squared. You get a positive 4 times 1 is going to be a positive 4. So much steeper right here than that slope of 1. Do the best you can. These points are luscious because x is equal to 0. Okay, 0 times anything is just going to be 0. So horizontal tangent line right there. Horizontal tangent line right there. And then you can see here x is equal to negative 1. So it's really going to be the opposite of the slopes we got over here. Plug them in separately if you want to. Here's the slope of positive 1. We're going to have a slope of negative 1, slope of positive 4, slope of negative 4. So it's not really too bad to actually draw out the slope fields. And then this is a cool conceptual problem. Use the slope field for the given differential equation to explain why a solution cannot have the graph shown below. Pause it. Think about it. Okay, when you come back here, there's a lot of different ways to speak about it. Some people talk about the horizontal asymptote being at y equals 1, and there's no horizontal asymptote at y equals 1 here. These slopes of 0 don't always indicate a horizontal asymptote. Could be a bunch of minimums or a bunch of maximums, something like that. The easiest way is to pick a point. Look at this point over here. Here's the point 1, 1, right? And we knew at 1, 1, the slope was equal to 0. Well, look at the point 1, 1 right here. Look at the slope, okay? You can see that the slope is not equal to 0, okay? So slope must equal 0 at 1, 1. So use the slope field to, explain why a solution cannot have the graph shown below. This slope is not 0, ... This slope is not 0. So you could try to do some things like that. You know, a lot of different ways to answer those questions. You know, right now we're kind of where the end of the video should be, okay? But I'm actually going to do this problem with you. Okay, so if you want to take some time, you know, a little bit later on to do it, you could pause it right now and try it. But they want you to find the particular solution. Let's just get a little bit of review. You know, if these videos are too long for you, I get it, okay? But you do have an AP exam coming up, most likely. More information about that today, believe it or not. I'm making this video on Monday, but you'll be watching it on Wednesday. So hopefully the AP will come out with some information by Thursday and we'll know a little bit more. But let's have some fun and separate here, cross multiply. Always put the dy on the left-hand side. dy times 1 is dy. Then we get equals x times y minus 1 quantity squared dx. And there's no way this thing right here is separated. We got to get the y's on the left-hand side. And you got to take the whole y minus 1 quantity squared. Divide by that on both sides. Same thing as multiplying by 1 over y minus 1 quantity squared. Don't be bringing the x over there, okay? He stays with the dx. And it's not an ln situation. If you integrate right now, you'd be integrating a quotient. The bottom is being raised to a visible power. So you probably want to write it as y minus 1 quantity to the negative 2 with respect to y. And now we can integrate this. You know, mental integration really comes in handy for differential equations, but you could use u substitution here, okay? If you have the base of a numerical exponent, it's not equal to one single letter, try to set that base equal to u. So u equals y minus 1. And then we get du over the derivative of u, which is 1, is equal to dy in this case. You just get that du is equal to dy, okay? So they call it u substitution, but they should really call it 2 substitution, because here this becomes u to the negative 2. Take out the dy, we get a du, right? Because if du over 1 is equal to dy, that means du is equal to dy. And here we could actually integrate x to the first, x squared over 2 plus c. Integrate this side, add 1 to the exponent, divide by that number. We don't have to worry about adding c because we put it on the right-hand side, but you do have to worry about taking out that u and putting back in the y minus 1. You know, if you're good at mental integration, you can just be like, yeah, I'm going to rewrite the y minus 1, add 1 to the exponent, divide by that number. But you're supposed to divide by the derivative of the inside. But the derivative of the inside is equal to 1, okay? If you divide by 1, it's not going to change the answer. So mental integration hath its, privileges, but nothing wrong with u substitution. Remember, I don't solve for y until I solve for c, and they gave me an inish condition, but you can get rid of the constants on the left-hand side. Always try to keep the left-hand side as clean as possible. I'll multiply my negative 1 on both sides. All right, these will cancel. I'm going to have y minus 1 quantity to the negative 1 power, which, by the way, is really 1 over y minus 1 quantity to the positive 1 power. Maybe you want to write it that way. Maybe you don't want to write it that way. We'll see what happens when you actually solve this thing. But here is equal to what? Negative x squared over 2, and then just plus c, because a negative 1 times a constant, just another constant. That's a pretty good general solution right there. Without these parentheses in the 1, because obviously it's not needed. But remember the inish condition. If f of 0 is negative 1, 0 comma negative 1 lies on this function. So if y is negative 1, 1 over negative 1 minus negative 1 equal to x is 0. Okay, and here we get a c on the right-hand side. 1 divided by negative 1 minus 1 is negative 2. 1 divided by negative 2, that's negative 1/2. That's our c. So let's actually take that, plug it back into our general solution. 1 over y minus 1 equal to negative x squared over 2 plus negative 1/2. Okay, so minus 1/2. And this is luscious because to solve for y here, you probably want to reciprocate both sides, but you can't do that until you have one single fraction on each side. And here you do have one single fraction because you have common denominators. So now we could actually take the reciprocal of both sides and get y minus 1 over 1. I'm not going to put the over 1 equal to 2 over negative x squared minus 1. And then you just got to add 1 to both sides. And then we're actually solved for y. And that's a beautiful particular solution right there. You could do things to make it look a little bit nicer, okay? But look, if it's a part 2, and your whole AP is probably going to be a part 2, free response, you could leave it like this. In a multiple choice, they might do this. They might actually factor a negative out of the bottom, which you might have already been thinking about. Then put that negative upstairs. And then you could actually write this as 1 minus 2 over the quantity x squared plus 1. So that's the most luscious way to look at it, but I wouldn't really worry about it at this particular point in time. Okay, so slope field is just a way to actually model a general solution. Okay, infinitely many particular solutions. For today, you should be able to actually plug back into the derivative, get those slopes, and draw those little snippets of tangent lines, and try to think if they gave you, an initial condition, like right here, they gave you the initial condition 0, comma -1, which is this point right here. Try to draw the particular solution. What would it look like? Maybe a little something like this. Do the best you can to actually follow the tangent lines. It's not always so easy to do. The best way to do it is to actually, solve and then graph something like this, which good luck graphing something like that without a calculator, but you could try it without your calculator. Okay, so that's our third lesson right there. Make sure you email me if you don't know what the heck is going on, or even just give me feedback. I like the videos. You can do this better with the videos. Whatever it is, okay, let me know. You know that I love you all very much, okay? We're going to get through this. We're going to be fine. And you're going to need to know this stuff, okay? Not just for the AP exam, but for the future, okay? And you guys can do whatever you want in your future. You're going to go on to great and wonderful things. All this virus nonsense will be over eventually. Until then, stay home, stay healthy, stay safe. This is Berto signing out. Adios.